Hey guys, it is Mrs. Rajewski. Today we are going to be talking about derivatives. So let's go ahead and start off with a lovely little warm-up. Today we're going to talk about calculating some slopes. Slopes, you say? Yeah. A little blast from the past, pre-algebra. Let's calculate the slope of the line that passes through each pair of points. So go ahead and pause the video, try and remember how you calculate slope, and solve these four, and then unpause it and we'll get started. Now, did you guys calculate the slope already? If you recall from pre-algebra, this is your first point and this is your second point. So you've got your first x value, your first y value, you've got your second x value, and your second y value. And you're going to calculate the change in your y values and divide it by the change in your x values. We calculate change using subtraction. So we're going to do 100 minus 4, the change in my y values, divided by 10 minus 2, the change in my x values. So I get 96 divided by 8, which is 12. So the slope here is 12, the slope in between these 2 points. And we can do the same thing for the rest of these problems. So we'll have 49 minus 4 divided by 7 minus 2. Ooh, that gives me 45 divided by 5, which is 9. So the slope between those 2 points is 9. And we'll continue. 9 minus 4 divided by 3 minus 2. This is going to give me 5 divided by 1, which is 5. And lastly, I've got 1 minus 4 and negative 1 minus 2. Well, 1 minus 4 is negative 3, and negative 1 minus 2 is also negative 3. So the slope in between these points is 1. So there you have it, a whole bunch of slopes. Now this is the average slope between these 2 points, and that's an important distinction. One of the things that we had to have in order to calculate the slope was we had to have change in these y and x values. So in order to have change, we had to have 2 points. If I only gave you 1 point, how would you be able to find the slope? Well, that's what a derivative does. It calculates the slope at just 1 point instead of 2. Let's continue. So a rate of change is the change in the dependent variable with respect to the independent variable, aka the slope. So as my x value, my independent variable, changes, my dependent variable changes along with it. An instantaneous rate of change is the change in the dependent variable with respect for the independent variable in a split second in time. So the problem is that when we're going to calculate this, as I was just talking about, if we are talking about a split second in time, we don't have 2 points. We've only got 1. And that is going to create this tangent line, this slope at a particular point. Let me see if I can get a little line here drawn. That would be a nice tangent line. So right here kind of looks like at that point that our graph is at that point just about to start shifting into a more positive, a steeper positive direction. So that might be my slope at that particular point. That line that I just created is called that tangent line, that slope at the point. So what is that tangent line? So let's not think about tangent from trigonometry. They are related, but we're not going to be thinking that hard at this point. So look at this picture. Obviously, it looks like right here at this point here, we've got our tangent line. They look really different. But if we zoomed in closer and closer and closer, zooming in, and zooming in, it will almost make that blue line, our original function line, start to look like it's getting straighter and straighter, so it's not as curvy, until they almost appear to be the same line. So this is a concept called local linearity. Okay, and as we zoom in closer and closer, they will look like they are the same line. And that's really awesome in calculus. So we need this because we want to study the exact behavior of graphs at every little point and section. And it's a lot easier to work with straight lines, right, linear functions, than it is to work with almost any other function. So we want to break things down so we're working with lots of little straight lines instead of lots of little curves. So these tangent lines are going to give us really cool like snapshots of what's happening at every point along our graph. So what if, because we already talked about how difficult it is to calculate slope if you only have 1 point versus 2 points. What if we chose 2 points that are really ridiculously close together and extremely close to the value? So that's what this little applet that I'm going to show you does. So here I've got this graph. So some kind of crazy graph here. And I've got 2 points, 1 and 1.5. This is creating a secant line. Come on, why is it giving me all this color? Here we go. So I want to know what's happening at 1. What is the slope of this graph at 1? 1.5 is pretty far away, and the line that's created doesn't look like it's the slope that's happening at 1. I mean, this one looks negative, and that one looks like it's positive, it's an increasing part of the graph anyway, so this seems far off. So right now, the difference between this x value and this x value is about a half. So what I want to do is I want to shrink that. I want to keep them closer together. So close that there's almost no space in between them, because the closer I can get these 2 points together, the more accurate that this line that's created is going to be to the slope at this particular point. So right now I'm like 0.08 apart, and that's pretty good. That's pretty close. But maybe I can get it closer. 0.01. Now there's 0 apart. My line has disappeared, but this is the tangent line. So check it out. If that's actually the slope at the point, I'm only a bit off here when I'm at a difference of 0.01 between this x value and 1.01, my next x value. But what I really want is not one that's pretty accurate. I want one that is exact. I want to find the slope of the point, right? At that point on my graph. So what I really want is no difference in between. So how can I do that? Well, it's actually not too difficult. I'm going to harness the power of limits. So what I'm going to do is take our slope formula. And this is pretty much our slope formula. It looks different, but it pretty much is our slope formula. And we're going to calculate basically the average between these points. So I'm going to take f of x plus a little bit, just x plus a little bit. And I'm going to subtract f of x, the original f of x value. And then I'm going to divide it by that little bit that I added, h. And I'm going to calculate the limit as h approaches 0, because if I just want it to be a little bit, just a little bit more, so I've got these 2 points, then I want that little bit to be so small it's basically nothing. That's what the limit does. It makes it nothing. This formula was not invented by me. Oh, no. This formula is called the definition of a derivative, or sometimes we call it the limit definition of a derivative. And it is also known as Newton's quotient or the first principles formula. So you will hear it a lot of different ways, but this is how you know that you need to calculate derivative using limits when you see one of these 3 things: the limit definition of a derivative, Newton's quotient, or the first principles formula. And what this does is it will calculate the instantaneous rate of change. It's almost like it's making up a second point that is zero away from your first point, if that makes any sense. So this is going to give you instantaneous rate of change, a derivative, or the slope of the tangent. Now, these are all equivalent statements. Instantaneous rate of change is a derivative. Instantaneous rate of change is the slope of the tangent line. And a derivative is the slope of the tangent line. So a derivative is simply a slope. I know a lot of times people get intimidated by calculus. It's got to be so hard. No, it's just a slope. And you've been doing slopes since the 7th grade. Now, I posted up on my website the link to this video, and I totally want you to watch it because calculus was basically invented simultaneously between Sir Isaac Newton and Leibniz. And it's fascinating, but Leibniz, he did a lot of writing and then also getting it published, whilst Newton did his work and kept it in his journals and had it published later. However, Newton was in charge of the Royal Academy of Sciences at the time, and he, because of his influence, was basically given a lot of the credit for calculus. So this is all going to be posted in my notes, so you can take a moment and read the PDF. There's a lot of information all about Newton. And then we've also got some more information about Leibniz. Leibniz. I don't know why I do that. So even though we give Newton so much of the credit for creating calculus, it's actually kind of interesting because nearly all of our notation, everything that we use for writing calculus, all came from Leibniz. So I guess he gets the last laugh. So the process of calculating a derivative is called differentiation. And the notation for a derivative, well, there's a lot of different notations for derivatives, let me just tell you. So you sometimes will see it written like this. And the way we read this notation is we say it's f prime of x. You could also call it the first derivative. A second notation called Leibniz's notation is this notation, which is said as dy dx. So dy dx. And it means the derivative of y with respect to x. So these are just two of some of the numerous notations. I'm going to try and use a variety of them so that you get used to see them, because your text and all your subsequent calculus classes are going to use all kinds of notations to represent a derivative, and I want you to be familiar with them. Okay, so let's go ahead and use first principles to calculate the derivative of y equals x squared when x is equal to -3. So I've got our steps that we're going to approach here along the side. I hope that that will help you as we start. So firstly, you do notice, of course, that we have a y, not an f of x. That's okay. Y is the same as f of x. So this is our f of x. Okay. And I'm going to calculate f prime. So we're going to take the first derivative of this function. So step number 1, we are going to substitute in x plus h for all the x's in the original function. So this is our original function. I have an x squared. I'm going to sub in x plus h there. So I will have x plus h instead of x squared. Easy peasy. That's what this piece says right here. Plug in x plus h everywhere you see an x. Next, we're going to subtract f of x. So we're going to subtract the original function. The original function was x squared. Then we're going to divide by h. And don't forget, we're calculating the limit as h approaches 0. All right, so Now it's time to simplify. So x plus h squared is going to pop up a lot, and it might just be easier if you know that x plus h squared expanded out is x squared plus 2xh plus h squared. You can use the distributive property if you want to like double check me and make sure that I'm right, but I'm pretty sure I'm right. So this will just save you time if you just expand it out using this. So we get x squared plus 2xh plus h squared minus x squared in the numerator, all divided by h down below. And what you're going to notice is some stuff is going to cancel out because x squared minus x squared is 0. So what I have left here is 2xh plus h squared. Now this is really important. There's going to be a moment, there will, when you can reduce, because I can't just calculate the limit as h approaches 0 here because I've got h in my denominator. If I substitute a 0 in here, I'm going to get a 0 in my denominator. That's going to fall to pieces. So, but what I can do is I can say, both of these terms have an h in common. So let's factor it out. This happens like every time, so be prepared. So I've got 2x, factor out the h, plus h squared. Well, I'm just going to factor one of those h's out, bring it to the front. I did already. All divided by h. Oh, hello. H divided by h. That's a fancy one. And so now I've got the limit as h approaches 0 of 2x plus h. And I can actually calculate that limit now by substitution. So if I substitute a 0 in for my h, I'm going to get 2x because I took the limit as h approached 0. So great. F prime of x is equal to 2x. And this is awesome. Your derivative is basically like a slope calculator. It's going to tell you the slope at every x value on f of x. So on the original function now, I have a new calculator that will tell me, oh, you want to know what the slope is at x equals -3? Boom, plug in -3, you got your slope. Oh, you want to know the slope at x equals 0? I got you. Just plug in a 0 here, bada bing, bada boom, you got yourself a slope at 0. So this is going to give you the slope like everywhere. It's a slope calculator. That's what the derivative is. So this problem actually does ask you for the slope where x is equal to -3. Fantastic. Let's take care of that now. At x equals -3, the derivative is equal to 2 times that x value, -3. And 2 times -3 is -6. So the slope of the parabola x squared at -3 is -6. And we're done. That's all limit is. But let's try it again. I promise that you will have a question on your test that asks you to use first principles to calculate a limit. So you're going to want to have a lot of practice. But I think once you do a couple of them, you'll start to get the hang of it. So again, here we go. I'm given a particular value of y, and I want to know the derivative when x is equal to 1. Okay, that's not too bad. Let's go for it. I've got, well, let's use a new notation. I'm going to use y prime. What? Yes, you can do that. So if you don't want to change it to f of x, you just want to continue using your y, you can put your derivative right on there. So that's the first derivative of y is equal to the limit as h approaches 0 of, now I need f of x plus h. So I'm going to substitute in x plus h everywhere I see an x in this function, and it's going to be crazy. So I got 2x squared, no, x plus h squared, minus x, no, minus x plus h, right? Everywhere we see an x, we're going to put x plus h. Then you're going to subtract, and you're going to subtract the whole entire original function. My whole entire original function was 2x squared minus x. Now, I do want you to notice how careful I'm being with my parentheses, because when we're subtracting, that minus sign is going to distribute to everything that we substituted. So please make sure that you're using parentheses like they're going out of style. And we're going to divide by h. Now, our next step, of course, is to simplify if we can. So we certainly can. I have the limit again as h approaches 0. I got to keep writing this until I actually calculate the limit. And I can't calculate the limit yet because substituting in 0 will put a 0 in my denominator. That's why we do this whole simplifying step first. So I've got 2 times, well, x plus h squared, again, is x squared plus 2xh plus h squared. And then we could say minus x minus h, I'm just distributing that negative, minus 2x squared, and a negative times a negative is a positive. Did you see? I've got a negative x and a positive x. Bye. All right, we're simplifying. Then we've got the limit as h approaches 0 of, let's do the distributive property here. I've got 2x squared plus 4xh plus 2h squared minus h minus 2x squared, all divided by h. Well, we've got some reducing that we can do here. 2x squared minus 2x squared, that makes a 0. It looks like nothing else is going to cancel out. However, I do notice that with what's left, everything has an h in it. So let's go ahead and factor out an h. I've got the limit as h approaches 0 of h times 4x plus 2h minus 1, all divided by h. Yes. Okay, I'm excited here because now I can finally get that h out of my denominator. And as soon as I do that, well, it is substitution time, my dears, because I can calculate the limit. So as h gets really, really close to 0, this is going to say 4 times x. There's no h there, so that's not going to have any effect. Plus 2 times, well, 0, right? It's getting really close to 0. So that's going to approach 0, okay? Minus 1, there's no h involved there. So that's just going to be 4x minus 1. That is y prime, our first derivative. This is great news because now I can tell you the slope of any point on this entire graph. Luckily, we don't need to know every single slope on this entire graph. We're just asked to find the slope at 1. So let's go ahead and calculate that. At x is equal to 1, the slope is equal to, I'm just going to substitute 1 right into our derivative. I've got 4 times 1 minus 1. Well, 4 times 1 is 4. 4 minus 1 is 3. So the derivative is 3. That's the slope at our point. All right, I got one more for you, and then we'll be done, I promise. Here we go. So for problem number 3, again, we're asked to calculate the derivative of y. And this time they've given us, a fraction. Oh no. That's okay. I'm actually glad to do this one with you because sometimes the fraction ones can be a little sneaky, but we practically learned all the math that we need to know to do advanced mathematics when we were in the 7th grade. So a lot of our 7th grade math skills are really coming into play here. So hopefully we'll be able to make those connections for you. So here we go. I'm going to calculate the derivative. I'm going to use Leibniz's notation, dy dx is equal to the limit as h approaches 0 of, I'm going to substitute in x plus h everywhere I see an x. So that's going to be 1 divided by x plus h squared. Little fraction bar, sorry. Then I have to subtract my original function, 1 divided by x squared, divided by h. Well, this looks crazy. It certainly does. So I need to simplify this numerator. That's our next step. So I've got two fractions being subtracted. One of the skills we learned in the 7th grade was in order, or one that we used a lot. In order to subtract fractions, we have to have a common denominator. And when we have polynomials for our denominator, it's pretty easy. This fraction needs to have a denominator of x plus h squared. So let's just multiply the top and bottom of our fraction by x plus h squared. It's basically a clever one, right? Because any number divided by itself is 1. I'm not really changing the value of this fraction. But over here, our first fraction, this one needs to have a denominator of x squared. So we can multiply the top and bottom by x squared. I know, you might be thinking, this still looks crazy, Mrs. Rajewski, and I'm not disagreeing with you. Sometimes it's going to look a little crazier before it looks a little bit neater. So here we go. X squared times 1 is x squared minus 1 times x plus h squared is x plus h squared, all divided by x squared times x plus h squared, all divided by h. Okay, so what I'm going to do now is I'm going to expand out the x plus h that's squared. So we've got the limit as h approaches 0, and we've got x squared minus, now x plus h squared is x squared plus 2xh plus h squared. And here we have it again. X plus h squared is x squared plus 2xh plus h squared. Please don't say that you can just cancel these out. You should know that you cannot just reduce these. This is being subtracted right now. This is being multiplied. This is a factor. This is a term. You cannot cancel out factors and terms, only factors. And don't forget your h. The whole entire thing is being divided by h. So I'm going to expand this a little bit further. I know, you're like, how far can one problem be expanded? This is about as crazy as it will get. So I have x squared minus, I'm going to distribute this negative. So I'm going to get minus x squared, haha, minus 2xh minus h squared. That negative is getting distributed through this whole entire polynomial. And then down below, I'm distributing x squared. So x squared times x squared is x to the 4th. And x squared times 2xh is a positive 2x cubed h. And x squared times h squared is a positive x squared h squared. Now we're dividing by h. Another way to divide is to multiply by the reciprocal. So that's what I'm going to do here. All right, check it out. We can start reducing a bit. So x squared minus x squared, not too shabby. There's nothing I can really cancel out here. And if you wanted to, you could distribute the h, but I recommend you don't, because see what I can do next. I've got the limit as h approaches 0 of, now my numerator, everybody's got an h, so I can go ahead and factor that out. Let's see. I'm just going to factor the h out. So I got h times negative 2x minus h. We've got x to the 4th plus 2x cubed h plus x squared h squared times 1 over h. And the reason why I left it like that is because it's actually pretty simple to just cancel out these h's. And wouldn't you know it, we are ready to calculate the limit. You see, Now if we substitute a 0 in for our h's, we are no longer going to cancel everything out in our denominator. So up on top, I'll be left with negative 2x. Well, minus 0, I don't need to write that. And as h approaches 0, x to the 4th is going to stay x to the 4th. But when h is 0, this piece cancels out and this piece cancels out. So I get that dy dx, my derivative of y with respect to x, is equal to negative 2x divided by x to the 4th. We can simplify that a little bit more too, which I'm going to. So we get dy dx is equal to negative 2 divided by x cubed. So we've got our derivative. But that's not enough because they wanted us to find out what the derivative was at x was equal to 2. So at x is equal to 2, dy dx is equal to negative 2 divided by 2 cubed. So I'm just substituting in 2 for my x value. And here we go, here we go, here we go. I get dy dx is equal to, well, negative 2 divided by 8, that's going to give me negative 1/4. Final answer. Now you might have been wondering this whole time, Mrs. Rajewski, why do you have a picture of a calculator with math 8 and type? What is this? Well, you can actually check your answer on your calculator. So let's go ahead and try that. So bust out your calculator. Here we go. Turn it on. And I want you to hit math. And option 8 should say something like n-deriv or something like that. So we're going to hit 8 or choose that option. And what should come up on your calculator should look something like this. Now, if you don't see it look exactly like this, you might not have an up-to-date graphing calculator. So just make sure that next time we see each other that you ask me to update your calculator. I'd be happy to do it. So I'm going to now, I made a little fraction, and I'm going to type in 1 divided by x squared. All right, move over. And now where we have x is equal to, this is where we're going to put in what point that we want to calculate the derivative at. So I want to calculate the derivative where x is equal to 2, so I'm going to put a 2 in there. And then the moment of truth, we hit enter. And I get negative 0.25. Well, this makes sense, right, to 3 significant figures because negative 1/4 is negative 0.25. And there you have it, how you can check it on your calculator. Haha. So there you go. Just to review, what we were doing in 7th grade math was calculating the average slope. So that's the slope between 2 points. What we learned how to do today was to calculate the slope when you only have one. And so it's often that these two formulas are mixed up by calculus students. Don't let that be you, okay? We also have average velocity. This is total distance divided by total time. And then instantaneous velocity. So that's the same thing. Velocity is our slope. And specifically, this is the slope. Instantaneous velocity is the speed at a very particular moment in time. But if you're talking about a trip or something like that, that would be your average velocity, not at a particular moment. That is your derivative, your slope there. So don't be confused, and make sure you ask questions if it doesn't make any sense. For your homework tonight, I'd like you to do Unit 6, Day 3, the homework on My Lab and Mastering, or you can do the homework assignment that's down below from our textbook. If you have access to My Lab and Mastering, that's what I want you to do. All right, you guys, I hope you have a phenomenal day, and I hope that you liked the video. Have a good one. Bye-bye.